What if the most profound testament to the power of creation is not what the universe has built, but what it has so conspicuously left undone? We have spent our entire existence as a species gazing upward, charting the architecture of the cosmos, connecting the dots of light into a story of magnificent construction. It is a story told in the language of gravity, written across 13.8 billion years of space-time. A story of matter triumphing over nothingness. In the grand cosmic theatre, we have always assumed the stage was full, that every corner was adorned with the splendour of existence, a testament to the relentless generative forces that exploded into being from a single infinitesimal point. We were convinced that wherever we looked, given a powerful enough eye, we would find something. Light, structure, a galaxy to call home. This belief is the very foundation of our cosmic perspective. It is a narrative woven from countless nights of observation and calculation, a tale of celestial bodies gathering into families, then into tribes, and finally into sprawling, glittering nations. You are part of one such family, our solar system, a tiny, almost insignificant household orbiting a single average star. This star, our Sun, belongs to a vast city of stars we call the Milky Way, a swirling disk of 200 billion suns, its spiral arms, elegant cascades of stellar nurseries, and ancient dying embers. From our quiet suburban neighbourhood within this galactic metropolis, we look out and see that we are not alone. Our city has neighbours, the great Andromeda Galaxy. A sister spiral larger than our own rushes toward us on a collision course that will unfold over the next 4 billion years, a gravitational dance of breathtaking scale. Together, our galaxies and a few dozen smaller companions form what astronomers call the local group, a small gravitationally bound community of island universes. Yet this is merely the beginning of the ascent. As we draw our perspective further back, these local groups reveal themselves to be but single threads in a far grander design. They are woven into the Virgo supercluster, a colossal aggregation of over 100 galaxy groups, and clusters a celestial kingdom spanning 110 million light-years. And even this incomprehensible dominion of matter and light is just one lobe of an even larger entity, a cosmic continent named Laniakea, our home supercluster, a structure so vast its name means immeasurable heaven in Hawaiian. This is the universe as we have come to know it, a magnificent luminous web. It is a structure of unimaginable beauty and complexity. Filaments of galaxies, shimmering chains of light stretch across the darkness, like the delicate strands of a spider's web connecting dense, brilliant nodes, where thousands of galaxies are packed together in violent, chaotic superclusters. These are the great intersections of the cosmic highway, blazing with the light of trillions upon trillions of stars humming with the energy of creation and destruction. Between these filaments lie the voids, the quieter, more sparsely populated regions of the cosmic countryside. We expected these, we predicted them. Computer simulations of the early universe governed by the elegant laws of gravity showed us that, as matter clumped together to form stars and galaxies, it would inevitably leave behind areas of lower density. These smaller voids, typically tens of millions of light-years across, are the natural consequence of cosmic evolution. They are the quiet valleys nestled between the towering mountain ranges of the cosmic web, essential components of the overall structure, providing the contrast that makes the brilliance of the superclusters all the more stunning. For decades, this map, this grand interconnected tapestry, seemed to confirm one of our most deeply held assumptions about the cosmos, the cosmological principle. The idea that on the largest scales, the universe is essentially the same everywhere. That no matter where you stood, no matter which direction you looked, you would see a similar distribution of galaxies, clusters, and voids. It was a principle of cosmic democracy, a comforting notion that our little corner of the universe was not special, that the same rules and the same general scenery applied from one end of creation to the other. It implied a universe that was, if not predictable, then at least fundamentally understandable, a cosmos that played by its own rules consistently across its entire unfathomable expanse. This principle became the bedrock of modern cosmology, the lens through which we interpreted the light from the farthest reaches of space, and the faint residual heat of the Big Bang itself. and for a very long time everything we saw from the nearest star to the most distant quasar seemed to reinforce this elegant, orderly vision of our reality. But the universe, it turns out, holds its secrets close. It allows us to peel back its layers one by one, but with each revelation it presents a new, more profound mystery, something that challenges not just our calculations, but the very intuition we have built over a century of cosmic exploration. It waits for us to become comfortable to believe we have grasped the fundamental pattern of its design, and then it shows us something that simply should not be there. Or in this case, something that should be there but isn't. Imagine a symphony, a majestic composition of infinite complexity and harmony, playing across all of time and space. Now imagine a sudden inexplicable silence. Not a rest, not a pause written into the score, but a total cessation of sound, a hole in the music so vast it threatens the integrity of the entire composition. A silence so profound and so prolonged that it becomes the only thing you can hear. This is what the universe showed us. As we continue to pull back our perspective, moving beyond Laniakea, beyond the intricate lacework of nearby superclusters, we begin to travel across distances that defy all human analogy. We are now journeying hundreds of millions of light years from home. The familiar constellations of our galactic neighbourhood have dissolved into a sea of anonymous points of light, each point a galaxy teeming with billions of stars. The cosmic web is in full view, a glorious effervescent foam of structure stretching in every direction. The cosmological principle holds. The universe appears uniform, a consistent masterpiece of gravitational artistry. We drift past the Hercules supercluster, a colossal wall of galaxies. We soar over the Sloan Great Wall, a filament of biblical proportions, one of the largest known structures in the cosmos. Everywhere we look, we find creation in its most majestic forms, and then we turn our gaze toward a specific unassuming patch of sky. A patch marked by a familiar guidepost for northern stargazers, the constellation Boötes the Herdsman. From Earth, Boötes is a comfortingly familiar kite-shaped pattern, anchored by the brilliant orange giant star Arcturus. It is a simple, ancient drawing in the sky, a piece of celestial folklore. But behind this gentle herdsman, behind the familiar twinkle of its stars, which are all comfortably within our own Milky Way galaxy, lies something else entirely. Something that has been waiting in the darkness for us to find it. As we push our perception past the foreground stars, venturing deep into intergalactic space, we begin a journey into the most unsettling landscape the universe has ever revealed. We cross a threshold. The music stops. The brilliant tapestry of the cosmic web, the endless rivers of light, the shimmering walls of galaxies. They all just vanish. You're now entering a region of space so empty, so utterly and profoundly desolate that it fundamentally breaks our understanding of the cosmos. At first it is merely disconcerting. The density of galaxies begins to thin, the brilliant superclusters recede into the distance behind us, and the journey forward becomes darker, quieter. The silence deepens. We are no longer flying through the glittering avenues of the cosmic city, but traversing a barren, forgotten wasteland. We push onward, 100 million light years. The darkness is palpable, 200 million light years. The emptiness becomes absolute, a physical presence, a smothering blanket of nothing. 300 million light years. We have now travelled a distance so immense that light itself, the fastest thing in the universe, would need more time to cross it than dinosaurs walk the earth. And there is still nothing. Absolutely nothing. This is the Boötes Void. But that clinical astronomical name feels wholly inadequate for what it represents. It has been called the Great Nothing, a far more fitting description for this monstrous anomaly. We are adrift in the heart of a cosmic desert, a spherical region of space so incomprehensibly vast and so starkly empty that it defies the laws of cosmic statistics. Its sheer scale is a brutal assault on the imagination. The latest measurements place its diameter at nearly 1 billion light years. Let that number settle. 1 billion years for a single photon of light to travel from one side to the other. If our own Milky Way galaxy, with its hundreds of billions of stars and its 100,000 light-year span, were a single grain of sand, the Boötes Void would be a chasm over 1.5 miles wide. You could fit tens of thousands of galaxies the size of our own into this space, yet we have found only a paltry handful, a few lonely isolated islands of light lost in a stupefying ocean of black. This is not one of the small predictable valleys we expected to find between the filaments of the cosmic web. This is a wound in the fabric of existence. It is a violation of the cosmological principle. An object this large and this empty simply should not exist according to our standard models of the universe's evolution. Gravity, the great architect of the cosmos, works slowly but surely, pulling matter together. Since the Big Bang, there simply has not been enough time for gravity to sweep a region, this gargantuan clean, to shepherd all the galaxies and all the gas into the surrounding walls, leaving behind such a pristine and monolithic emptiness. It's like finding a perfectly circular desert 1,000 miles wide on Earth, with every single grain of sand having been meticulously moved to form a perfect mountain range at its border, all in the span of a single afternoon. It's not just unlikely, it feels impossible. It suggests that either our understanding of gravity is incomplete, or some other unknown force was at play in the dawn of time, carving out this titanic bubble of nothing. Its discovery in the early 1980s was not a sudden dramatic moment, but a slow, creeping realization of a horror among a small group of astronomers. They were undertaking the first large-scale three-dimensional surveys of the universe, using the subtle shift of a galaxy's light toward the red end of the spectrum to measure its distance. As they pointed their telescopes toward the constellation Boötes and began plotting their map galaxy by galaxy, a terrifying blank space began to emerge in their data. At first they thought it was an error, a problem with their instruments, a flaw in their methodology. They checked and rechecked their findings, but the void remained. It was real. They had stared into a patch of sky that should have been teeming with thousands of galaxies and found a void so complete it looked like a hole had been punched through the universe itself. This is the place we have come to call the empty zone. Our journey in this series is an investigation into this cosmic enigma. We will seek to understand not just what the Boötes Void is, but what it means. What does its existence tell us about the birth of our universe and the forces that shaped it? How could such a structure form, and what does it imply about the grand cosmic architecture we thought we understood? This is a detective story written on the grandest of all possible scales, and the crime scene is 1 billion light-years wide. We will travel back in time to meet the scientists who first stumbled upon this impossible emptiness, to share in their disbelief and their slow acceptance of a universe far stranger than they had ever imagined. We will venture into the heart of supercomputers, where cosmologists run epic simulations desperately trying to conjure a universe that can naturally produce such a monstrous feature, tweaking the laws of physics to see if they can replicate this cosmic ghost. And finally, we will confront the most tantalizing and profound question of all: is this zone truly empty? Or is its emptiness merely a failure of our own limited perception? Could this void be filled with something we cannot see, a vast reservoir of dark matter, a domain where the mysterious force of dark energy holds absolute sway, pushing everything apart? Could it even be evidence of something more exotic, the bruised remnant of a collision with another universe, a scar from a cosmic event we don't yet have the physics to describe? The empty zone challenges us to redefine one of the most basic concepts in our vocabulary. It forces us to ask what nothing really is. On Earth, a vacuum is never truly empty. It is a roiling sea of virtual particles, a quantum foam of potential. In the deepest reaches of space, in the heart of this colossal abyss, we may find that what appears to be nothing is in fact the key to understanding everything. This is not just a story about a lack of matter. It is a story about the limits of our knowledge and the enduring power of human curiosity. It is about our relentless quest to map the unknown, to make sense of the silence, as well as the noise. The Boötes Void is a silent testament, a monolithic monument to the universe's capacity to surprise us, to humble us, and to inspire in us a profound and unending sense of awe. To understand this colossal anomaly, this great and silent province of the cosmos, we must first return to that pivotal moment in our history. The moment a handful of scientists meticulously plotting points of light on a chart realized they had found the edge of a precipice and saw the impossible staring back. What does it mean to create a map? For millennia, it was an act of claiming, of understanding, of turning the wild and the unknown into something ordered, something human. We drew lines around continents, charted the terrifying moods of our oceans, and in doing so we believed we were charting reality itself. But our reality we were about to discover was a far grander and stranger territory than any earthly explorer could have ever conceived. And the map we were just beginning to draw would reveal not just what was there, but the equally profound and terrifying mystery of what was not. By the dawn of the 1980s, we were no longer just looking at the sky, we were starting to look into it. For the first time our gaze had true depth. The flat, glittering tapestry of the night, a celestial portrait that had captivated humanity since its infancy, was finally being peeled back to reveal a third dimension, the unfathomable abyss of cosmic distance. The key that unlocked this new perspective was a phenomenon as simple as the changing pitch of a passing siren. Redshift. The elegant stretching of a light waves as a source, in this case a distant galaxy, rushes away from us. For decades, Edwin Hubble's monumental discovery of this redshift had told us our universe was expanding, that the star cities scattered across the cosmos were all flying apart. But now a new generation of astronomers wanted to use it for something more. They wanted to turn this cosmic echo into a surveyor's tool, a measuring stick of impossible length. By meticulously capturing the faint ancient light from a galaxy, and measuring precisely how much its signature had been shifted towards the red end of the spectrum, they could calculate its speed, and by extension its distance from us. Do this for one galaxy, and you have a single point in space. Do it for 1,000, for 10,000, and you begin to build something that has never existed before a three-dimensional map of the known universe. You transform the celestial sphere into a true cosmic volume populated by luminous islands floating in an ocean of time. This was the grand, audacious ambition. The prevailing theory of the day, the cosmological principle, offered a comforting prediction of what they would find. On the very largest scales, it suggested the universe should be fundamentally uniform. It should be homogeneous, the same in every location, and isotropic, the same in every direction. Like a fine, even mist, galaxies should be sprinkled throughout the cosmos with a predictable, almost placid consistency. Of course, we knew they clumped together. Our own Milky Way is part of the local group, a small gravitationally intimate family of galaxies. And we knew the local group was just a humble suburb of the much larger Virgo supercluster, a sprawling metropolis of thousands of star systems. But the idea was that if you zoomed out far enough, these local lumps and bumps would smooth out, revealing a grand underlying uniformity. The universe in its ultimate form was thought to be orderly, predictable, almost serene. It was into this grand theoretical calm that a small determined team of cosmic cartographers prepared to venture armed with little more than light glass and an insatiable curiosity. Their base of operations was the Kitt Peak National Observatory, a temple to the stars perched high in the Sonoran Desert of Arizona. Here, under skies so dark they seemed to have a physical weight. Robert Kirshner of Harvard University, along with his colleagues Augustus Umla Jr., Paul Schechter, and a young, brilliant postdoc named Stephen Scheckman, embarked on a project of excruciating patience. Their goal was simple to state but monumental to execute: to chart a few small patches of the northern and southern skies, to meticulously measure the redshifts of every faint smudge of a galaxy their telescope could find. This wasn't glamorous work. It was a slow, painstaking process of cosmic archaeology, digging through layers of deep-time photon by precious photon. Night after night they would guide the telescope, a colossal steel beast, moving with silent balletic grace, to lock onto a target, a whisper of light that had been travelling towards them for hundreds of millions of years, since long before the dinosaurs walked the earth. Imagine yourself there, in the quiet hum of the control room, the only light coming from the glowing monitors. Outside, the universe wheels in profound silence. Inside, you're trying to catch its ghost. The light from a single distant galaxy, a city of 100 billion suns, is focused down to a point so faint it is utterly invisible to the human eye. This trickle of ancient energy is then passed through a spectrograph, a sophisticated prism that splinters the light into its constituent colours, its rainbow barcode. On this spectrum, dark absorption lines appear, the chemical fingerprints of the elements inside that galaxy's stars. It is the precise position of these lines nudged from their true place by the relentless expansion of space that holds the secret. It is the key to that galaxy's distance, its coordinate on the great invisible map. For each galaxy, this process took hours. Hours of waiting, hours of collecting a signal that was barely more than noise, and then once the data was captured, they would move the telescope by a fraction of a degree and begin the entire process again. They were building their map one point of light at a time. The first few dozen galaxies went into their survey, their positions dutifully recorded. 100, 200. Slowly, painstakingly, a picture began to emerge from the darkness. As expected, they saw clumps and clusters. They saw filaments, those luminous bridges of galaxies that we now know connect the great superclusters. Their map was beginning to trace the tendrils of what we call the cosmic web. In one of their survey fields, a wedge of sky pointed in the direction of the unassuming constellation Boötes the herdsman. They charted a galaxy at a distance of some 600 million light-years, then another nearby at 620 million, then one a little farther at 680 million. The data points were falling into place, revealing the expected architecture. The cosmological principle, it seemed, was holding up. The universe was behaving just as the textbook said it should. But then something strange began to happen. Or rather, something strange stopped happening. As they pushed their survey deeper into that same patch of sky beyond about 700 million light-years, the galaxies simply vanished. The steady drumbeat of discovery fell silent. The data stream, which had been reliably spitting out new, more distant points of light for their map, ran dry. At first it was a curiosity, a statistical blip. Perhaps they had just hit a small, unusually sparse patch. So they kept observing, pointing the telescope to adjacent locations within the Boötes field, hunting for the faint smudges they knew should be there. They pushed their instruments harder, straining for longer periods, trying to capture ever more distant photons from the abyss. But they found nothing. The silence was deafening. Night after night the result was the same. A profound, unnerving and statistically impossible emptiness. The team checked their equipment. Was there a flaw in the spectrograph? Was the detector malfunctioning, human error, instrument failure? These are the first ports of call for any scientist confronted with an anomaly. It is always more likely that you have made a mistake than that you have discovered a flaw in the fundamental nature of the universe. They recalibrated. They cross-checked their results. They meticulously reviewed their logs and their pointing accuracy. But every test confirmed their methodology was sound. The instruments were working perfectly. The lack of data wasn't an error. The lack of data was the data. Slowly, over weeks and then months, a chilling realization began to dawn in the cool, quiet air of the observatory. They hadn't just found a small gap between clusters. They had stumbled upon a hole in the cosmos, a region of space so vast and so barren it defied all their expectations. In a cone of space extending from 700 million light-years out to nearly 1 billion light-years, where there should have been hundreds, if not thousands of galaxies, there was next to nothing. Just an immense vacuous gulf. It was a whisper of nothingness that screamed through their data. It was a presence defined entirely by its absence. A ghost on their map. Robert Kirshner and his team found themselves in an extraordinary position. They were the first explorers to stand at the edge of an impossible desert, one whose scale was difficult for the human mind to even process. Let us try. Our Milky Way galaxy is about 100,000 light-years across. Our local group of galaxies spans a few million light-years. The Virgo supercluster, our home superstructure, stretches for over 100 million light-years. These are already distances that dwarf human comprehension. But the void they had found, this colossal bubble of emptiness in the direction of Boötes, appeared to be nearly 300 million light-years in diameter. It was a volume of space so gargantuan that you could fit thousands of superclusters like our own inside of it, and they would rattle around like marbles in a cathedral. If our own Milky Way had been located at the centre of this void, we would not have known other galaxies even existed until the 1960s. The night sky would have been a near-perfect blackness, a desolate vista offering no hint of the true sprawling grandeur of the cosmos beyond its borders. When they finally published their findings in 1981, The paper landed with a quiet thud in the astronomical community. The title was sober and academic: A Million Cubic Megaparsec Void in Boötes. The question mark was telling. It betrayed their own sense of disbelief, a hedge against the sheer audacity of their claim. The initial reaction from their peers was predictably one of deep skepticism. It had to be a mistake, an artifact of a small survey size. They hadn't looked hard enough. The galaxies were there, they were just too faint to be seen. The idea of such a monstrous hole in the fabric of the cosmos seemed absurd. It flew in the face of the elegant, ordered universe predicted by the Cosmological Principle. It suggested that the cosmic mist wasn't a fine, even spray after all, but was instead more like a coarse foam, a collection of immense bubbles, whose thin luminous walls were studded with galaxies enclosing vast regions of profound desolation. But Kirshner's data was robust, and as other surveys began to chart other parts of the sky, the anomaly of the Boötes Void was not explained away. Instead, it was confirmed, and it wasn't alone. Astronomers began finding other voids, vast empty realms that pockmarked the cosmic landscape. The universe, it turned out, was not the uniform homogeneous space we had imagined. It possessed a staggering unexpected architecture, an immense sponge-like structure of luminous filaments, dense walls and monumental nodes where superclusters gathered like great capital cities, and separating all of it, defining all of it, were the voids. These weren't just gaps in the map. They were a fundamental structural component of the universe itself, the silent dark counterpoint to the brilliant symphony of the galaxies. The discovery of the Boötes Void was a watershed moment. It shattered a pillar of cosmological thinking and forced us to see the universe in an entirely new light. It was the moment our map went from being a simple catalogue of objects to a true structural blueprint of reality. The universe was not a random scattering of points, but a delicate interconnected web, a tapestry woven from matter and gravity over billions of years. And like any tapestry, the empty spaces between the threads were just as important as the threads themselves. They gave the whole structure its shape, its form, its character. The empty zone in Boötes was not an error or an absence. It was a clue. It was the first glimpse of an unseen blueprint, a signpost pointing toward a deeper understanding of the powerful invisible forces that had sculpted the cosmos since the dawn of time. This colossal emptiness, once an anomaly that provoked disbelief, now posed a series of profound and urgent questions. If the universe began as a smooth, hot, dense soup after the Big Bang, what force could have acted as a cosmic plough pushing matter aside on such an incredible scale? How could gravity and attractive force be responsible for creating regions so utterly devoid of the very matter it seeks to pull together? What secrets lie dormant within that silent, starless expanse, a place where the expansion of the universe proceeds almost completely unchecked by the pull of matter? The Boötes Void was no longer just a hole in a map. It had become a destination, a laboratory for understanding the birth and evolution of cosmic structure itself. And as our technology grew more powerful, we would prepare to turn our most sensitive eyes towards that patch of darkness, not to search for what was there, but to listen, with breathtaking intensity, to the story that its silence had to tell. The initial data points were not a mistake. They were a whisper from a void so profound, so utterly vast that the human mind struggled to anchor itself against the scale of the revelation. Robert Kirshner and his team, having pointed their telescopes towards the constellation, Boötes had anticipated the gentle, predictable peppering of galaxies they saw everywhere else. Instead, they had found nothing. But this nothingness was not a simple gap. It was a structured, three-dimensional emptiness with terrifying implications. The first cautious estimate, a void perhaps 20 or 30 million light-years across, was already a cosmic oddity, a statistical improbability that warranted a closer look. So they looked again, pushing their instruments to their limits, gathering more precious photons from the deep, hunting for the faint spectral signatures of distant island universes. With every new redshift measurement, the picture grew not clearer but emptier. Each plotted galaxy, instead of filling in the void, seemed to trace its boundary, defining the shoreline of an impossible ocean of darkness. That initial 20 million light-year hole was revealed to be merely the near edge of the chasm. The survey pushed deeper into cosmic time and the emptiness stretched on unbroken. The void was not a sphere. It was a monstrous amorphous cavern in the fabric of reality. The number that began circulating in astronomical circles was 250 million light-years. To comprehend that scale, you must imagine our own Milky Way galaxy with its 100 billion stars and our nearest major neighbour Andromeda. Then picture the entire local group of galaxies to which we belong. Now imagine a space so colossal that you could fit thousands of local groups inside it end to end and still have room to spare. This was a desert of incomprehensible proportions. The news rippled through the community not as a triumphant discovery but as a deeply unsettling anomaly. For decades, cosmology had been built upon a foundational idea known as the Cosmological Principle. It was an assumption of modesty, really, the notion that our place in the universe is not special. It stated that on the larger scales the cosmos is homogeneous, and isotropic meaning it looks roughly the same everywhere and in every direction. It should be a uniform tapestry of galaxy clusters and filaments, a predictable distribution of matter. But the Boötes Void was a violent rejection of that principle. It was a scar, a wound in the otherwise smooth face of the cosmos. It was as if you had surveyed a forest and found deep within it a perfectly circular desert 10 miles wide. It simply should not have been there. The prevailing models of galaxy formation, which depicted gravity as a slow, patient shepherd, gradually herding matter together over billions of years, had no mechanism to explain such a colossal evacuation of matter. Gravity could build galactic cities, but it was not supposed to be capable of excavating continental voids. The questions became immediate and urgent. Was Boötes a freak of nature, a 1 in a trillion statistical fluke that we just happened to find? Or was it a sign that our entire map of the universe was fundamentally wrong? The only way to find out was to map more of the sky with the same three-dimensional precision. It was a Herculean task. The redshift surveys of the 1980s were painstaking endeavours, requiring long exposures on single galaxies one by one. But driven by this unnerving discovery, astronomers pushed forward. Projects like the CFA2 redshift survey led by Margaret Geller and John Huchra began to systematically chart the nearby universe. They weren't just looking for voids, they were trying to create the first truly comprehensive map of our cosmic neighbourhood. What they unveiled was revolutionary. As they plotted galaxy after galaxy, a stunning and entirely unexpected structure began to emerge from the data. The universe was not a uniform mist of galaxies. It wasn't a random scattering of points of light. It possessed a definite architecture, a magnificent and intricate pattern that no one had predicted. They found that galaxies were not distributed evenly, but were instead organised into immense interconnected structures. There were long-flowing rivers of galaxies which they named filaments. Where these filaments intersected, they found dense, brilliant knots of matter, the great galaxy clusters, the bustling metropolises of the cosmos. And surrounding these filaments and clusters, defining them, were the voids. Suddenly, the Boötes Void was not a complete outcast. The surveys revealed other empty regions like the local void adjacent to our own galaxy group and the massive Sculptor Void. While none of these rivaled the sheer monolithic scale of the Boötes Leviathan, their very existence proved that emptiness was not an anomaly. It was a fundamental component of the universe's design. The cosmos, it turned out, was a sponge. It was a complex web-like lattice of matter surrounding enormous near-empty bubbles. This breathtaking new picture of reality came to be known as the cosmic web. Imagine blowing soap bubbles in the dark. The iridescent film of the bubbles where all the soap and water reside is where you find the galaxies. These soapy walls are the filaments and clusters shimmering with the light of a trillion suns. But the vast volume inside the bubbles, the dark empty space between the films, represents the cosmic voids. Our universe, seen on the grandest of scales, is mostly this interior emptiness. The galaxies, the stars, the planets, everything we had ever known or studied were confined to the shimmering, gossamer-thin walls of this cosmic foam. We were living on the edge of the abyss. This new model, the cosmic web, was both a stunning confirmation and a source of profound theoretical crisis. It confirmed that the Boötes Void was not a mistake, but rather the most extreme example of a common cosmic feature. Yet it threw the problem of its formation into even sharper relief. If the universe was supposed to have started from the near-perfect uniformity we observe in the cosmic microwave background radiation, the afterglow of the Big Bang, then how could such dramatic structures have formed? The standard model of cosmology, powered by gravity alone acting on normal matter, was put on the stand. Calculations were run, simulations were coded, and the results were always the same. It simply didn't work. Given the age of the universe, a little under 14 billion years, there had not been enough time for gravity's gentle pull to sweep regions hundreds of millions of light years across so completely clean. It's a problem of speed. Galaxies on the edge of a void would need to be moving away from its centre at incredible velocities to evacuate such a volume in the available time. Standard gravitational collapse. The process of matter clumping together is a slow bottom-up affair. Small clumps form first, then merge into bigger ones, which eventually grow into galaxies and clusters. This process would leave behind a far more uniform distribution of matter, with many smaller voids and a much less defined web-like structure. It could not under any circumstance produce a behemoth like Boötes. The universe the models predicted was a gentle rolling landscape. The universe we were actually observing was a dramatic topography of soaring mountain ranges and plunging abyssal canyons. The disconnect was a chasm in our understanding. The cosmic web was an observational fact, but it required a sculptor far more powerful and efficient than gravity, acting on visible matter alone. It demanded a missing ingredient, an invisible hand shaping the cosmos on the largest scales. This was no longer just about a single empty patch of sky. This was about the fundamental forces that govern the evolution of the entire universe. The very existence of these voids hinted that the universe was home to a ghost, an unseen form of matter, perhaps that did not shine or interact with light, but whose gravitational influence was paramount, carving out the great voids and weaving the luminous filaments of the web. And just as the community was grappling with this theoretical impasse, the observations of Boötes continued. New, more powerful telescopes and more sensitive instruments peered deeper into its heart. Over the years, that already mind-boggling figure of 250 million light-years was revised. Upward. Always upward. The void was deeper and wider than anyone had dared to imagine. As astronomers refined their techniques and expanded their surveys, the true, horrifying scale of the great nothing began to crystallize. It wasn't 250 million light-years across. It wasn't even 350 million. Later studies, including data from the Sloan Digital Sky Survey, would push its estimated diameter to a staggering 1 billion light-years. A billion. A region of space so large that light itself, the fastest thing in the universe, would take 1 billion years to cross from one side to the other. This number broke cosmology. It shattered the comfortable confines of the cosmological principle on a scale that was impossible to ignore. A structure covering such a significant fraction of the observable universe could no longer be dismissed as a local anomaly. It was a headline feature. It suggested that the universe might not be the same everywhere, that there could be domains and structures so vast they challenge our most basic assumptions. You could fit 10,000 Milky Way galaxies side by side in the space of the Boötes Void, and they would be lost, tiny sparks swallowed by an oppressive monolithic darkness. Within this volume, where our models predicted there should be tens of thousands of luminous galaxies, we have found only a paltry few dozen lonely isolated islands of light in a sea of utter desolation. The struggle to reconcile this immense emptiness with our models of creation became the central battleground of modern cosmology. The discovery of the Boötes Void and the subsequent mapping of the cosmic web it inspired was a classic scientific revolution in the making. It began with an observation that didn't fit a loose thread in the tapestry. But as scientists pulled on that thread, the entire picture of the universe began to unravel, revealing a new, far stranger, and more magnificent reality hidden beneath. It was a reality dominated not by the light we can see, but by the darkness we cannot. The very existence of this billion light-year chasm demanded a new physics, a new understanding of the ingredients of our universe. It was a silent, empty testament to the fact that everything we could see, every star, every galaxy, every nebula was merely the foam on a cosmic ocean, whose true depths we were only just beginning to suspect. The empty zone was no longer just a location. It was a question aimed at the very heart of existence. What built this cathedral of nothingness And what invisible architecture holds the rest of the universe in its place? But what if this chasm in the heavens was not a mistake? What if this profound and unsettling vacancy, stretching across 1 billion years of cosmic travel, was not an aberration at all, but a prophecy fulfilled? For decades, the discovery of the Great Nothing had stood as a monument to the unknown, a tear in the fabric of our assumptions about the universe. It felt wrong. It felt impossible. Yet deep within the equations taking shape in the minds and on the blackboards of cosmologists, a radical new story was being written. A story in which such immense voids were not only possible but utterly breathtakingly inevitable. The shock of finding the Boötes Void was about to be replaced by an even more profound realization that we were living in precisely the kind of universe that would build such a thing. The void was not a monster lurking in the dark. It was a feature of the architecture, a load-bearing pillar of emptiness in the grand cosmic cathedral. To understand how, we must rewind the clock. Not just millions or billions of years, but all the way back to the very first fraction of a second after the Big Bang. Here, in an infant cosmos smaller than a single atom, the universe was a maelstrom of unimaginable energy. It was almost perfectly smooth, a uniform sea of quantum potential. Almost. But in the realm of the quantum perfection is a myth. The very laws of physics dictate a constant simmering uncertainty. Even in a perfect vacuum, particles and antiparticles flash into and out of existence, a phenomenon known as quantum fluctuation. Think of it as the universe trembling on the smallest possible scale. In that primordial state, these fluctuations were infinitesimally tiny ripples of density, places where for a fleeting moment there was fractionally more stuff than somewhere else. These were the seeds, the microscopic, almost non-existent seeds of everything that would ever be. Under normal circumstances, these fleeting ripples would have cancelled each other out, leaving behind a blandly uniform cosmos devoid of any structure. But the early universe was anything but normal. In a moment of truly cataclysmic violence, a process we call cosmic inflation kicked in. The universe swelled, expanding faster than the speed of light, growing from a subatomic point to the size of a grapefruit in less than the blink of an eye. This hyper-expansion did something miraculous. It grabbed those tiny quantum-scale fluctuations and stretched them, amplifying them to astronomical proportions. The microscopic hills and valleys of the quantum foam were instantly magnified into vast regions of slightly higher and slightly lower density, now woven into the very fabric of space-time itself. The blueprint for the cosmic web, with its filaments, its clusters and its voids, was drawn in the universe's first breath. From that moment on, a familiar force took command: gravity. But gravity, we have learned, does not play fair. It operates on a brutal principle we might call the rich get richer. Those regions that inflation had gifted with a fractionally higher density, even by just 1 part in 100,000, now possessed a slightly stronger gravitational pull than their surroundings. This tiny advantage was all they needed. Over millions of years, they began to gently tug on the matter around them. More matter meant more mass, which meant a stronger gravitational field, which in turn pulled in even more matter. It was a cosmic feedback loop, a slow-motion gravitational avalanche operating on a scale that beggars belief. The overdense regions became the universe's great collection, points the basins into which the rivers of cosmic matter would inevitably flow. And this is the crucial insight, the key to understanding the existence of the Boötes Void. For every region where matter was accumulating, there had to be a region from which that matter was being taken. If gravity makes the rich richer, it must by definition make the poor poorer. The slightly underdense regions, those primordial valleys stretched out by inflation, began a very different journey. With a weaker gravitational pull to start with, they began to lose their scarce reserves of matter to their wealthier, more massive neighbours. It wasn't a passive process. They weren't simply leftover spaces, they were actively excavated. A great gravitational tide swept through the cosmos, draining these areas, hollowing them out, creating a deepening emptiness that grew with every passing eon. Every galaxy cluster that formed a glittering jewel of light and mass did so at the expense of the space around it, casting a vast gravitational shadow. The voids, then, are not holes in the universe. They are the galactic graveyards, the quarries from which the great cities of the cosmos were built. This elegant picture, however, was missing two colossal ingredients. The first was an invisible giant, a substance that accounts for over 80% of all matter in the cosmos, yet interacts with light in no way whatsoever: dark matter. Our models of structure formation simply collapsed without it. The gravitational pull of the visible matter we could see, the stars, the gas, the dust, was utterly insufficient to create the vast cosmic web in the 13.8 billion years the universe has existed. Dark matter provided the missing mass. It was the invisible scaffolding laid down in the early universe that began clumping together long before normal matter could. It created the deep gravitational wells, the cosmic riverbeds, that guided the flow of hydrogen and helium, directing them to the filaments and nodes where galaxies would later ignite. Without dark matter, gravity's engine would have been too weak. With it, the formation of the cosmic web was not just possible, but an inevitable consequence of the initial conditions. The rich-get-richer effect was put on steroids, accelerating the growth of clusters and consequently deepening and expanding the voids from which their material was drawn. The second ingredient was even more mysterious, a force working in direct opposition to gravity. For billions of years, the cosmic expansion that began with the Big Bang had been slowing down, restrained by the mutual gravitational pull of everything in the universe. But several billion years ago, something changed. The expansion began to accelerate. We call the cause of this acceleration dark energy, a persistent repulsive force embedded in the fabric of space itself. And for the voids, this was a game changer. As the universe expands, the gravitational pull of matter within a dense cluster becomes more and more concentrated, easily overpowering the repulsive push of dark energy in that localized region. But in the vast, underdense voids, there is very little matter to hold things together. Here, dark energy reigns supreme. It acts like a constant, inexorable pressure, pushing the walls of the void, the great filaments of galaxies, farther and farther apart. The voids began to swell, to grow, to merge with one another, dominating the cosmic landscape. Dark energy was the final catalyst, turning the voids from large empty regions into the colossal billion light-year chasms we see today. They are not just growing, they are winning the cosmic tug-of-war. This grand theoretical framework, born from quantum physics and cosmology, was beautiful. It was compelling. But was it true? How could we possibly test a hypothesis that spanned the entire age and breadth of the universe? The answer lay in creating new universes from scratch, not in a lab, but inside the world's most powerful supercomputers. Beginning in the late 20th century, cosmologists embarked on one of the most ambitious projects in the history of science to simulate the evolution of the cosmos. They would feed the machine the essential ingredients, the laws of gravity, the measured amounts of dark matter and dark energy, and a set of initial conditions based on those tiny quantum fluctuations observed in the cosmic microwave background. Then they would press run and watch. Watch as billions of virtual particles, each representing a vast cloud of dark matter, dance to the tune of gravity over billions of years of simulated time. The results were a staggering, world-altering triumph. Out of the simple physics and the random noise of the beginning, a universe uncannily like our own began to take shape on the screen. Filaments emerged from the digital fog, weaving themselves into a luminous web-like structure. At their intersections, dense knots of matter coalesced, forming the halos that would host galaxy clusters. And between them all, vast dark and empty regions began to open up, expanding and merging. The simulations were predicting the voids. They were showing with breathtaking clarity that if you start with the known laws of physics, a universe filled with immense vacancies is the natural default outcome. It was a moment of profound vindication. The voids were no longer cosmic freaks. They were the expected consequence of our most fundamental understanding of the universe, and this brought the scientific community full circle back to that unnerving patch of darkness in the constellation Boötes. The Great Nothing was no longer an anomaly to be feared, but a specimen to be studied. It became the ultimate laboratory, a crucible in which to test the limits of these new cosmological models. The simulations produced a whole menagerie of voids with a predictable statistical distribution of sizes. Most were modest, perhaps a few tens of millions of light years across. Larger ones were less common. But the simulation showed that given a large enough volume of space, the chance formation of a truly gargantuan void was statistically possible, even if exceptionally rare. The question became terrifyingly simple. Was the Boötes Void, in all its billion light-year immensity, a 1 in a trillion fluke, or did it fit comfortably within the predictions of our standard cosmological model? Answering this required painstaking work, comparing the digital universes born in silicon with the one we actually inhabit. It meant running hundreds, even thousands of simulations each, a slightly different cosmic roll of the dice, to see how often a void of that scale would naturally arise. The tension was palpable. If the simulations could never produce something as extreme as the Boötes Void, it would signal a catastrophic failure in our understanding. It would mean that some crucial piece of physics, some unknown force or ingredient, was still missing from our cosmic recipe. But as the data poured in and the statistical analyses were refined, a consensus began to emerge. A void as large as the one in Boötes is indeed an outlier. It is the cosmic equivalent of finding a 10-foot-tall human, but it is not impossible. It sits at the far edge of the bell curve, a rare but perfectly natural consequence of gravitational evolution in a universe dominated by dark matter and dark energy. Our theories, it seemed, were powerful enough to account for even the most extreme structures the cosmos could throw at us. Yet just as one mystery was solved, another more subtle one came into focus. Because the Boötes Void is not, as its popular name suggests, completely empty. Sprinkled throughout that unimaginable volume like a handful of lost ships on a featureless ocean are a few dozen galaxies. 60 have been catalogued so far. If you were to travel through the void, you would fly for tens of millions of years at the speed of light before encountering even one. They are the loneliest galaxies in the universe, and for scientists they are priceless. These isolated systems represent a unique control group in the grand cosmic experiment. For their entire existence, they have been shielded from the chaos that defines life in a crowded cosmic metropolis. A galaxy like our own Milky Way is a product of violence and cannibalism. It has grown by merging with and devouring countless smaller galaxies over billions of years. It is constantly battered by gravitational tides from its neighbours and fed by streams of intergalactic gas flowing along the cosmic filaments. The galaxies of the Boötes Void have known none of this. They are cosmic hermits evolving in almost perfect isolation. Their growth has been stunted, starved of the steady diet of gas and smaller galaxies that fuels vigorous star formation. As a result, they offer us a pristine glimpse into what a galaxy becomes when left entirely to its own devices. When we study them, we find they are different. They tend to be purer in their structure, often exhibiting beautifully simple, undisturbed spiral or elliptical shapes. They have fewer heavy elements as they haven't been repeatedly enriched by the supernova explosions of multiple merged galactic populations. Their star formation is a slow, quiet affair, not the frantic bursts seen in colliding galaxies. They are in a very real sense living fossils from an earlier, simpler time in the universe's history. By comparing these lonely wanderers to their cousins in densely packed clusters, we can begin to untangle the profound influence of environment on destiny. We can quantify exactly how much a galaxy's neighbourhood shapes its size, its colour, its chemistry, and its ultimate fate. Each of these faint solitary smudges of light is a Rosetta Stone helping us translate the complex language of galactic evolution. They teach us that to understand what something is, you must also understand what it is not. To comprehend the frantic dynamic life of a galaxy within the cosmic web, we must first listen to the profound silence emanating from the heart of the void. To stand at the edge of such an abyss is to feel an intellectual vertigo, a pull towards a question that reshapes our entire cosmic perspective. What happens when you remove a billion light-years of everything? When you carve out a region of the cosmos so vast it defies our terrestrial sense of scale? What are the consequences for the universe that remains? You might imagine that such a colossal void is a passive feature, a silent, empty stage upon which the grand cosmic drama unfolds elsewhere. But the truth is infinitely more complex and far more unsettling. This empty zone is not a spectator. It is an active, dynamic, and powerful participant in the evolution of the cosmos, its profound emptiness exerting a subtle, yet relentless influence that we are only just beginning to comprehend. This is the startling realm of void dynamics, a field that forces us to reconsider the very nature of cosmic expansion and our place within it. For centuries we have held to the cosmological principle, the reassuring idea that on the vastest scales, the universe is homogeneous and isotropic. Essentially that it looks the same in every direction and that the laws of physics are consistent everywhere you go. It is the bedrock assumption upon which our entire understanding of the universe is built, the foundation for our models of cosmic evolution. But a billion light-year hole punches a rather significant exception into that comforting uniformity. Within this gravitational desert, the familiar rules begin to bend. Here in this profound underdensity, the cosmic tug-of-war between gravity and dark energy plays out with a different and perhaps terrifying intensity. Across the universe, in the dense filaments and superclusters of the cosmic web, gravity acts as a powerful brake pulling matter together, resisting the accelerating expansion driven by dark energy. But inside the void, there is almost no matter to provide that gravitational brake. Dark energy, the mysterious repulsive force pushing the universe apart, essentially has the floor to itself. The result is a bizarre and counterintuitive phenomenon. The void isn't just expanding along with the rest of the universe, it appears to be expanding faster. It empties itself out more aggressively, pushing the few galaxies at its edge away from its centre with an ever-increasing velocity. The void in a very real sense grows, becoming emptier and more dominant over cosmic time. This creates a local distortion in the Hubble flow, the smooth uniform expansion of space-time we thought we understood. Imagine the universe as a vast rising loaf of bread with galaxies like raisins being carried apart as the dough expands. Now picture a massive air bubble baked into that loaf. The dough around that bubble will be stretched thinner, expanding more rapidly in that local region than the denser parts of the loaf. Our own Milky Way galaxy, it turns out, sits in a relatively underdense region, a smaller void known as the KBC void, which itself may be adjacent to this even more colossal supervoid. We are living on the outskirts of the great cosmic desert, and this single inconvenient fact might just be the key to solving one of the most profound crises in modern cosmology, a schism that has split the astronomical community in two. It is a problem known simply and ominously as the Hubble tension. The Hubble constant is arguably the single most important number in our cosmic narrative. It tells us how fast the universe is expanding, and by extension, it allows us to calculate its age, its history, and its ultimate fate. For decades, astronomers have pursued this number with a relentless fanatical precision, employing ever more sophisticated methods to pin it down. And in their pursuit, they have uncovered a dreadful paradox. Two different impeccably precise methods of measuring the Hubble constant are giving us two different and completely incompatible answers. One method involves looking at the local present-day universe. Astronomers build what they call the cosmic distance ladder, a painstaking step-by-step process of measuring distances to nearby objects and then using them as standard candles to calibrate distances farther and farther out. They use pulsating stars called Cepheid variables and exploding stars called type supernovae, cosmic lighthouses of known brightness, to gauge the distances to galaxies. By measuring a galaxy's distance and the speed at which it is receding from us, you can calculate the current rate of cosmic expansion. Team after team has refined this method, eliminating uncertainties, and they have converged on a very specific number. The universe, they say, is expanding at about 73 kilometers per second per megaparsec. But there is another way to measure this constant, a method that does not look at the universe today, but at the universe in its infancy. This technique involves studying the cosmic microwave background, or CMB, the faint residual afterglow of the Big Bang itself. This light, which has been travelling towards us for 13.8 billion years, carries an imprint of the universe when it was just 380,000 years old. It is a baby picture of the cosmos, and encoded within its subtle temperature fluctuations is a treasure trove of information. By applying our best understanding of physics, the standard cosmological model, to this primordial map, scientists can predict what the expansion rate should be today. It is a calculation of breathtaking scope, projecting the evolution of the entire cosmos forward in time from its very first moments, and it gives us a completely different answer. The CMB data analysed by the Planck satellite with astonishing precision predicts that the Hubble constant should be nearly 67 km per second per megaparsec. The discrepancy is not a minor statistical error. The error bars on these two measurements do not overlap. The odds of this being a random fluke are less than 1 in a million. It is a 5 sigma tension, a chasm in our understanding. It means that either the astronomers measuring the local universe are systematically wrong, or the cosmologists interpreting the ancient universe are systematically wrong. Or, and this is the most tantalizing possibility, our entire standard model of cosmology, the grand theory that has guided our understanding for a half-century, is missing something fundamental. This is where the void re-enters the story, not as a curiosity but as a potential saviour. What if the problem isn't with our telescopes or our theories, but with our address? What if our particular location in the cosmos is biasing our measurements? If we live in a region that is significantly emptier than the cosmic average, an area experiencing a faster local rate of expansion, then when we look out at nearby supernovae, they would appear to be flying away from us faster than they really are on average. Our cosmic neighbourhood would be a local pocket of accelerated expansion, a fast lane on the cosmic highway. Our measurements of 73 would be correct for our patch of the universe, while the CMB's prediction of 67 would be the correct global average for the cosmos as a whole. The void, this billion light-year zone of nothingness, could be the physical mechanism that resolves the Hubble tension. It could be the missing piece of the puzzle, the environmental factor we failed to account for. We thought we were measuring a universal constant, but we may have only been measuring our own peculiar empty corner of it. The very structure that seemed like an anomaly could be the key to restoring order, a profound irony that nature seems to favour. Yet the void's influence does not stop there. Its gravitational shadow stretches all the way back to the dawn of time, potentially distorting the very relic radiation we use to understand our cosmic origins. It forces us to look again at that baby picture of the universe, the cosmic microwave background, and question if we are seeing it clearly. For nearly 2 decades, cosmologists have been haunted by a particular feature in that map of the infant cosmos. Amidst the subtle random mottling of warmer and cooler patches, there lies one region that is anomalously, inexplicably cold. It is a vast frigid spot on the sky, larger and colder than almost any simulation of the standard model of cosmology can produce. It has been dubbed with a chilling simplicity the CMB cold spot. It is an outlier, a statistical improbability that has stubbornly refused to go away as our measurements have improved. It is a sour note in the otherwise perfect symphony of creation's first light. For years, scientists sought explanations. Perhaps it was a statistical fluke, a 1 in 1,000 chance, that would eventually be understood. Perhaps it was a flaw in our instruments, or our analysis, a smudge on the cosmic lens. But as mission after mission confirmed its existence, a more radical idea began to take hold. What if the cold spot isn't primordial? What if it isn't a feature of the early universe at all, but rather something more recent, something happening between the ancient CMB and our telescopes today? In 2014, astronomers mapping the distribution of galaxies in the sky pointed their instruments in the direction of the cold spot, and they found nothing. Or more accurately, they found a profound and shocking lack of things. Stretching across that very same patch of sky directly between us and the cold spot lay the largest structure ever discovered, the Eridanus supervoid. A colossal emptiness, a billion light-years across. The alignment was too perfect to be a coincidence. The coldest part of the ancient sky was perfectly framed by the emptiest part of the modern universe. The connection seemed undeniable, but the mechanism was far from obvious. How could an empty space or region defined by its absence leave a cold fingerprint on light that was merely passing through it? The answer lies in one of the strangest and most beautiful consequences of Einstein's general relativity, a phenomenon known as the integrated Sachs-Wolf effect. It is a story about the journey of a single photon of light across billions of years of expanding, evolving space-time. Imagine a photon from the cosmic microwave background, a particle of ancient light that has been travelling unimpeded through space for 13.8 billion years. As it traverses the cosmos, its path will inevitably lead it through regions of higher density, like galaxy clusters, and regions of lower density, like voids. When this photon enters a massive structure like a supercluster of galaxies, it falls into a gravitational well. As it falls deeper into this well, it gains energy just like a marble rolling downhill. This gain in energy manifests as a tiny shift in the photon's frequency. Towards the blue end of the spectrum, it experiences a blue shift. Then, as the photon climbs back out of the other side of the gravitational well, it must expend that energy, losing it to escape the cluster's gravity. This results in a corresponding redshift. In a static, unchanging universe, the energy gained on the way in would be perfectly cancelled out by the energy lost on the way out. The photon would emerge from its journey completely unchanged. But our universe is not static. It is expanding, and that expansion is accelerating, driven by dark energy. And this is where the magic happens. During the hundreds of millions of years it takes for our photon to cross a vast supercluster, the universe itself has continued to expand. This expansion, powered by dark energy, stretches and flattens out the gravitational well. So when the photon climbs out the hill it has to climb is now shallower than the one it rolled down. It doesn't have to expend as much energy to escape as it gained when it entered. The result is that the photon emerges with a net gain in energy. It is slightly more blue than when it started. Structures like superclusters actually heat up the CMB light that passes through them. Now consider the opposite journey, the journey of a photon through a supervoid. As the photon enters the void, it is effectively climbing out of the denser surrounding universe and up onto a gravitational hill, a region of lower than average gravity. It loses energy as it climbs this gentle cosmic slope, experiencing a slight redshift. It then coasts across the billion light-year expanse of the void. During this immense travel time, the relentless push of dark energy causes the void to expand and become even emptier. The gravitational hill effectively sinks and flattens beneath the photon. When the photon finally reaches the other side and begins to roll back downhill into the denser universe, the slope it descends is now less steep than the one it climbed to get in. It regains some energy, but it doesn't regain as much as it originally lost. The photon emerges from the void with a net loss of energy. It is slightly redder, which for the CMB means it appears slightly colder. A supervoid acts as a cosmic refrigerator for ancient light. This integrated Sachs-Wolf effect, predicted by theory decades ago, provides a stunningly elegant explanation for the CMB cold spot. The inexplicable chill in the baby picture of the universe may be nothing more than the gravitational shadow of the colossal void that lies in the foreground. It is a breathtaking synthesis of cosmology, connecting the largest and oldest things we can observe in a single coherent narrative. We seem to have found the answers. The void dynamics could potentially resolve the Hubble tension, and the integrated Sachs-Wolf effect could explain the cold spot. The standard model of cosmology, while stretched, seems to hold. It would be a neat, satisfying conclusion. But nature is rarely so simple, and for some scientists these explanations, while elegant, are not quite enough. The measured cooling effect from the integrated Sachs-Wolf effect, according to our current models, is too weak. It can account for some of the cold spot's chill, but not all of it. The spot is still colder, still deeper than the void's shadow should be able to make it. The discrepancy remains a nagging whisper of doubt, and it is in this gap between what our theory predicts and what our telescopes see that the most profound and revolutionary ideas are born. What if the connection between the void and the cold spot is not merely one of shadow and light? What if it is something deeper, something that signals a crack in the very foundation of our standard model? What if this colossal void is not just a feature in our universe, but a scar on our universe? Some physicists have dared to propose a truly mind-bending hypothesis, one that steps firmly into the realm of science fiction. They suggest that the cold spot and the supervoid could be the bruised lingering remnant of a collision between our universe and another. In the theoretical landscape of eternal inflation and string theory, our universe may not be the only one. It might be just one bubble in a vast frothing sea of other universes, a cosmic foam of countless realities, each with potentially different laws of physics. Occasionally these bubble universes might collide. Such a cataclysmic event, a literal clash of realities, would leave a lasting mark, a localized disruption in the fabric of space-time and the distribution of energy. Could the CMB cold spot be the point of impact? a cosmic bruise on the infant universe from which matter and energy were violently repelled, creating a zone of emptiness that would then grow over billions of years into the super void we see today. It is a staggering, almost unimaginable idea that we could be seeing the fossilized evidence of contact with a parallel world printed on the sky. There are other equally exotic possibilities. Perhaps the voids are home to a different form of dark energy, one that behaves in ways our models do not predict. Perhaps they are windows into higher dimensions, their gravitational influence bleeding through into our own. These are ideas on the farthest frontiers of human thought, pushing the boundaries of what can be tested and known. They transform the void from a simple absence of matter into a laboratory for new physics. The empty zone becomes the most interesting place in the universe precisely because it is so barren. It is a place where the fundamental forces of nature are laid bare, where the subtle whispers of cosmic evolution become screams, and where the evidence for realities beyond our own might just be waiting. The consequences of this single empty space continue to ripple outwards, challenging our most cherished assumptions and forcing us to confront the possibility that the universe is far stranger and far larger than we have ever dared to imagine. And as we stare deeper into that darkness, we find it is not empty at all. It is full of questions, full of mysteries, and full of the promise of a revolution that could rewrite everything we know about our cosmic home. And so, we were left adrift, confronted by an impossible gulf of nothing. An anomaly so profound, so utterly defiant of our expectations, that it threatened to unravel everything we thought we knew about the grand, sweeping structure of the cosmos. The Boötes Void was not just an absence of galaxies, it was a profound and unsettling absence of answers. For decades, this chasm of darkness stared back at us from the maps, a cosmic question mark hanging in the celestial void. Our telescopes, peering ever deeper, only confirmed its scale, its emptiness, its silent rebuke of our neat and orderly theories. The path forward, the way to solve this colossal riddle, would not be found by building a larger lens to gather more light. The key, it turned out, was not to look farther out into the deep, but to look deeper inward into the very source code of reality itself. The solution was to build another universe. Humanity, in its quest for understanding, has always built models from stone circles charting the sun to intricate clockwork orreries. But the challenge of the cosmic web required something new, a tool of unimaginable power and complexity. We needed a crystal ball, not of glass, but of pure computation. We needed to forge a cosmos in silicon, a digital genesis where we could plant the seeds of creation and watch them grow. This revolutionary approach is known as an N-body simulation, a name that belies its breathtaking ambition. The N simply stands for the number of bodies or particles involved. In the early days, and was in the thousands. Today it can be in the trillions. Imagine a virtual cube of space, a universe in a box ready to be filled with the ingredients of existence. First you pour in the laws of physics, unbreakable and absolute. The foundational one, of course, is gravity, the great sculptor, the patient artist of cosmic structure, as dictated by Einstein's general relativity. Then you add the cosmic expansion, the inherent outward stretch of space-time, the engine that has been driving everything apart since the Big Bang. These are the rules of the game, the software that will run our new reality. But what of the players? What is the matter we place inside? Here we must be guided by our most fundamental observation of the infant universe, the cosmic microwave background radiation. That faint, persistent glow from the dawn of time which you've seen mapped in exquisite detail is the blueprint, the starting photograph for our simulation. It tells us that the early universe was astonishingly, almost perfectly uniform. A smooth, hot, dense soup of matter and energy, with only the most minuscule fluctuations in temperature and density, tiny ripples on an otherwise placid cosmic ocean, no more than 1 part in 100,000. These tiny imperfections, these almost imperceptible whispers of structure, are the seeds that we carefully plant in our digital cosmos. They are the starting positions for our trillions of particles, and now for the most crucial ingredient of all, the one that makes the whole recipe work. We don't just add the familiar matter of stars and gas, the baryonic matter we are made of. If we did, the simulation would fail spectacularly. Gravity acting on normal matter alone is far too weak, far too slow to build the majestic cosmic web we see today in the mere 13.8 billion years it had. The resulting virtual universe would be a diffuse, nearly featureless wasteland bearing no resemblance to the star-drenched reality we inhabit. No, to build the universe we actually see, we must add the ghost. We must pour into our simulation the dominant yet invisible component of cosmic matter, the universe's unseen scaffolding cold dark matter. This is the CDM in our standard model of cosmology. It is a substance that feels the pull of gravity, but interacts with nothing else. It does not shine, it does not reflect, it does not block light. It is a silent, ghostly shepherd, whose only instinct is to gather, to clump, to patiently draw all things toward it. In our simulation, the vast majority of our embodies are dark matter particles. They are the true architects of structure, the gravitational anchors around which the visible universe of galaxies will eventually coalesce. Finally, we add the last and perhaps most mysterious force. We add a term to our equations that represents the accelerating expansion of the universe, a persistent space-stretching energy woven into the fabric of the cosmos itself. This is the cosmological constant represented by the Greek letter lambda, and so our model is complete lambda cold dark matter, or lambda CDM. It is the culmination of a century of cosmological discovery, a precise recipe for a universe encapsulated in lines of elegant yet powerful computer code. The ingredients are measured, the physics is encoded, the seeds are sown. All that is left is to press run and witness 13 billion years of cosmic history unfold before our eyes in a matter of weeks. The simulation ignites. Time, compressed and accelerated, begins to flow. For the first few 100 million virtual years, the universe expands and cools. The cosmic box grows, and within it a silent gravitational war begins. The outward push of cosmic expansion tries to pull everything apart, while the inward pull of gravity, amplified by the immense reserves of dark matter, fights to bring things together. It's a battle fought in near silence in the darkness before the first stars. The initial density ripples those tiny seeds from the cosmic dawn are the battlegrounds. Where the density was ever so slightly higher, dark matter begins to clump. These clumps become the gravitational seeds, the overdense regions. Like nascent whirlpools in a cosmic river, their gravitational pull intensifies as they attract more and more dark matter from their surroundings, and as they grow, they begin to starve their neighbours. The regions that started out with even a slightly lower density find themselves at a disadvantage. Their precious matter is relentlessly stolen, siphoned away by their more massive, greedier neighbours. The rich get richer, and the poor get poorer. This is the fundamental engine of cosmic structure formation, a runaway gravitational process. Slowly, miraculously, a structure begins to emerge from the initial smoothness. The dark matter doesn't just form isolated clumps, it is pulled into vast interconnected tendrils like the gossamer threads of a spider's web. We see the birth of the great cosmic filaments, rivers of dark matter flowing across millions of light years. Where these filaments intersect, they form dense, brilliant knots. These nodes are the junctions of the cosmic superhighways, the places where dark matter concentration is highest. And clinging to this immense invisible skeleton, like dew on a web at dawn, the ordinary matter, the stuff of stars and planets and people, is pulled along for the ride. The dense nodes of dark matter become the birthplaces of massive galaxy clusters, great cosmic cities blazing with the light of 1 trillion suns. The long flowing filaments become the chains and walls of galaxies, connecting the clusters in a luminous, galaxy-strung tapestry. The simulation, born from pure mathematics and observation, is painting a portrait of the universe that is hauntingly, breathtakingly familiar. It has built the cosmic web. But it is in the spaces between the threads that the final stunning revelation awaits us. As the filaments and clusters grow, pulling in ever more material from their surroundings, the regions they leave behind are not merely empty, they are actively evacuated. They are stretched, hollowed out and expanded by the relentless cosmic expansion, a process amplified by the very growth of the structures around them. What begins as a slightly underdense region is ruthlessly emptied, its sparse matter drawn away to the glittering walls of the growing web. And in the simulation we watch them form. Vast, dark, spherical bubbles begin to inflate in the spaces between the filaments. They swell and merge, growing larger and emptier with each passing billion years. They are the cosmic valleys to the filament's mountain ranges, the quiet wildernesses next to the bustling galactic cities. They are the voids. And as the cosmologists, the digital creators of this pocket universe, zoomed in on the statistical distribution of these simulated structures, they felt a tremor of profound recognition. The simulation wasn't just producing small, modest voids. It was naturally, inevitably, and repeatedly generating monsters. Bubbles of emptiness, hundreds of millions of light years across, appeared defined by sharp galaxy-lined walls, just as the observational surveys had shown. And there, emerging from the cold logic of the code, was the unmistakable signature of the Boötes Void itself. Not as a freak of nature, not as an anomaly, but as a standard, predictable, and even necessary feature of cosmic evolution. This was the moment of climax, the turning point in our understanding. The great void, the object that had so perplexed and challenged us, was suddenly transformed from a cosmic problem into a triumphant confirmation. It was the ultimate proof that our model of the universe was not just successful, but profoundly correct. The sheer existence of a billion cubic light-year chasm like the Boötes Void was no longer a mystery to be explained away. Instead, it became one of the most powerful pieces of evidence we have for the entire lambda CDM paradigm. The simulations demonstrated that to get a universe that looks like ours with its brilliant clusters and filaments, you must also get the great voids. The two are inseparable two sides of the same cosmic coin. The emptiness is the necessary counterpart to the structure. It is the cosmic excavation site from which the material to build the galaxies was dug. You cannot have one without the other. Our theories, which had once struggled to account for this gaping hole in the cosmos, were now showing us that such a hole was a direct and foreseeable consequence of the fundamental physics that govern everything. The size of the void, its extreme emptiness, the way galaxies timidly line its edges, all of these features once so baffling were now being reproduced with stunning fidelity inside supercomputers that had been fed only the initial conditions of the Big Bang, the law of gravity, and the observed quantities of dark matter and dark energy. It was as if we had discovered an ancient, undeciphered text, and suddenly, a single new insight allowed us to read the entire manuscript flawlessly. The Boötes Void was the Rosetta Stone for the large-scale structure of the universe, and the story it tells is one of an intricate and majestic cosmic dance, choreographed by invisible forces over billions of years. Imagine the universe as a vast expanding ballroom. In the beginning, the dancer's particles of dark matter and normal matter are spread almost perfectly evenly across the floor. But some dancers are infinitesimally closer to one another. Gravity, the silent choreographer whispers to them, come together. As small groups form, their collective gravitational pull becomes stronger, and they begin to attract more dancers from the surrounding floor. The clumps grow, evolving into waltzing groups that sweep through the ballroom, pulling even more partners into their embrace. These are the filaments and clusters, but as these popular groups form vast empty spaces are cleared on the dance floor, these are the voids. Now introduce the final dancer, the most enigmatic of all dark energy, the lambda. It isn't a particle, but the dance floor itself. And the floor is not static. It is expanding, and its expansion is accelerating. This doesn't break up the tightly knit groups of dancers who are held together by their strong mutual gravity. But it has a dramatic effect on the empty spaces. The accelerating expansion takes hold of the voids, stretching them, inflating them like balloons, pushing the walls of galaxies ever farther apart. This is why the voids dominate the volume of the universe today. They are the expanding heart of the cosmos, the embodiment of dark energy's relentless push. The Boötes Void in its colossal emptiness is not a void of information. It is a pristine laboratory for studying the nature of dark energy, a place where its effects are laid bare on the grandest possible scale. The void is not nothing. It is a testament to the elegant and deeply intertwined play of cosmic forces that have shaped our home. The profound realization that dawns from these digital universes is that nothing about the cosmic web is arbitrary. The placement of every galaxy cluster, the path of every filament, the size and location of every great void, none of it is random happenstance. It is the elegant, deterministic and predictable outcome of the simplest possible starting conditions evolved forward through time by a handful of fundamental physical laws. If you were to run the simulation again with the exact same initial seeds, you would grow the exact same universe time after time. A void, akin to Boötes, would form in the same region. A cluster like coma would coalesce in its designated place. There is a majestic inevitability to the structure of the cosmos, a hidden order beneath the apparent chaos of the sky. The universe on its largest scales is not a random spray of matter. It is a single coherent structure, a gravitational organism that grew from a quantum seed according to a precise genetic code. That we beings confined to a fragile planet can write down a set of equations and use them to birth a virtual cosmos that so perfectly mirrors the one we see in our telescopes is perhaps the most astonishing achievement in the history of science. It confirms that we are not just passive observers of the cosmic drama, but that we have begun to read the script itself. The emptiness, once a source of confusion and doubt, has become the ultimate symbol of our understanding. It is the quiet, dark and beautiful proof that we are at long last beginning to understand the intricate dance of creation, undefined. And so we return to where our journey began, not with a map of what is there, but with the terrifying, exhilarating chart of what is not. We have walked the lonely shores of this incomprehensible emptiness, this silent continent of cosmic night we call the Boötes Void. We have moved beyond the initial shock of its discovery, that sudden dizzying realization that a portion of our universe was simply missing. That feeling first felt by Robert Kirshner and his team as they stared at their wedge of the cosmos was the feeling of humanity confronting a scale of structure so profound it bordered on the absurd. Their initial search for galaxies was like listening for a symphony in a soundproof room, an experience that fundamentally challenged our assumptions of a universe filled more or less uniformly with light and life and matter. From that perplexing anomaly, that great nothing that haunted the constellation of the herdsman, a new understanding has been forged. The void is no longer a cosmic error, a glitch in the celestial code. It has become a cornerstone, a keystone in the grand arch of modern cosmology. Its existence is not a violation of the rules, but rather their most dramatic and spectacular confirmation. It is what the universe must create to build the very structures we inhabit. For every glittering supercluster, for every delicate shimmering filament of the cosmic web, there must be a corresponding emptiness from which its substance was drawn. The empty zone is the quarry from which the cathedrals of the cosmos were built, the silent mould that gave shape to the brilliant cast of creation. To understand it is to understand the fundamental architecture of everything. Think of the delicate, almost impossibly patient forces at play. For billions of years, gravity acted as a tireless microscopic sculptor on a galactic scale. It sent out its subtle, irresistible call across vast tracts of the infant universe, a call that was answered not with a sudden clap, but with the slowest, most majestic migration in cosmic history. Trillions upon trillions of tons of hydrogen and helium, guided by the unseen scaffolding of dark matter, began to drift. They moved away from the regions that would become the voids and towards the nascent intersections of the cosmic web. This was not a violent explosion pushing matter out, but a gentle, persistent persuasion pulling matter in. The Boötes Void wasn't carved out. It was simply evacuated. It is the breathtaking result of an exodus that lasted for eons, a cosmic ghost town whose residents left for the promise of brighter, denser cities of light. Its profound emptiness stands as a silent monument to this grand interplay of cosmic forces. Gravity, the great gatherer, provided the initial impetus, amplifying the tiniest quantum fluctuations from the dawn of time into regions of slightly higher and lower density. Dark matter, the universe's invisible skeleton, formed the gravitational basins into which ordinary matter would inevitably fall, creating the gravitational rivers that flowed towards the future galactic superclusters. But as this process of construction unfolded, another more mysterious force was beginning to assert its dominance over the cosmic landscape. Dark energy, the intrinsic energy of space itself, began its inexorable work of expansion. Within the dense, gravitationally bound filaments and clusters, its effect was negligible, easily overpowered by the mutual attraction of matter. but here in the underdense regions like the Boötes Void it found its kingdom. With so little matter to resist it, dark energy's repulsive push became the ruling force. It took the already emptying spaces and stretched them, expanding them like a cosmic lung, making them larger, emptier, and more isolated. The Boötes Void, therefore, is not just a relic of the universe's past structure formation. It is an active and growing feature of its present and its future. It is a pristine laboratory, a controlled environment, on a scale we could never dream of building, where the subtle, universe-altering effects of dark energy are laid bare for us to study. Its very existence and continued growth are among the most powerful pieces of evidence we have for this enigmatic force that is accelerating the expansion of our universe. This transformation of the void from a mere curiosity to a crucial scientific tool marks the next chapter in our cosmic exploration. Looking ahead, these great empty zones are no longer places to be ignored on our maps. They are the primary destinations for our most ambitious investigations. They offer us a unique window into the deepest mysteries of physics, a place to ask questions that are impossible to answer amidst the noisy, crowded confines of a galaxy. The future of cosmology lies not just in studying the brightest lights, but in plumbing the deepest darkness. For instance, we are embarking on a new era of cosmic cartography with instruments of unprecedented sensitivity. Telescopes like the Euclid Space Mission and the Vera C. Rubin Observatory are designed to map the positions and shapes of billions of galaxies, creating a three-dimensional atlas of the universe with staggering fidelity. Their primary mission is to trace the cosmic web in exquisite detail, but in doing so, they will inevitably map its inverse, the voids. By charting the precise boundary shapes and the subtle sub-voids within larger structures like Boötes, we can measure the history of cosmic expansion with unparalleled precision. As light from the ancient cosmic microwave background radiation travels across the universe to reach us, its path takes it through these vast empty spaces. When a photon enters a void, it loses a tiny bit of energy climbing out of the gravitational well of the surrounding matter. As it travels through the expanding void, space-time itself stretches beneath it. When it finally exits, the gravitational wall it must climb is now further away, and the photon doesn't regain all the energy it lost upon entry. This phenomenon, the integrated Sachs-Wolf effect, leaves an almost imperceptible cold spot on the CMB. By correlating the maps of voids from our new telescopes with the temperature maps of the CMB from probes like the Planck satellite, we can measure this effect across the sky. The strength of this correlation directly tells us about the behavior of dark energy. Does its repulsive force change over time? Is it a constant feature of space, an Einstein's cosmological constant? Or is it something more dynamic, a quintessence that evolves as the universe ages? The voids are our cosmic proving ground. Their immense scale amplifies these tiny effects, turning the entire universe into a single, magnificent particle physics experiment. We can watch how the voids grow and merge over billions of years of cosmic time, a direct measure of the cosmic tug-of-war between gravity's pull and dark energy's push. The final outcome of that battle will determine the ultimate fate of our universe. But the promise of the voids extends even further into territory that challenges the very foundations of our understanding of gravity itself. For a century, Einstein's theory of general relativity has been our guide to the cosmos, passing every test we have thrown at it with flying colours. From the bending of starlight around the sun to the spiralling dance of merging black holes, its predictions have been flawlessly confirmed. Yet all of these tests have been conducted in regions where gravity is relatively strong. What if the theory is incomplete? What if, on the largest, most desolate scales of the universe, gravity behaves differently? Some theories of modified gravity propose that the accelerating expansion we observe isn't due to a mysterious dark energy at all, but is instead a sign that our theory of gravity needs revision. How could we possibly test such a radical idea? We would need a place where the gravitational field is exceptionally weak, where any tiny deviation from Einstein's equations might become detectable. We would need a place like the Boötes Void. Inside this vast emptiness, the gravitational environment is purer and simpler than anywhere else in the cosmos. By studying the motions of the few lonely galaxies that drift through its interior, or by precisely measuring how the light from distant quasars is bent as it passes near the edge of the void, a technique called weak gravitational lensing, we can perform the most sensitive test of general relativity ever conceived. If we see galaxies moving in unexpected ways or light bending more or less than predicted, it could be the first tremor of a seismic revolution in physics. It might be the first clue that we need a new story to tell about the force that shapes the universe. The void in its perfect stillness could be the very place where Einstein's brilliant theory finally meets its match, pushing us towards a deeper and more complete understanding of reality. This is the profound legacy of that empty patch of sky. It began as a source of bewilderment, a blank page in our book of the cosmos. Now we see it as perhaps the most important page of all. It is the context for everything else. It is the silence that gives the music its meaning, the canvas that allows the masterpiece to be seen. The universe, it turns out, speaks just as eloquently through its absences as it does through its grand assemblies of matter and light. The glittering filaments of the cosmic web show us what gravity can build, but the cavernous voids show us the raw power of the underlying principles of the cosmos, the initial conditions set at the Big Bang, and the relentless accelerating expansion driven by dark energy. They are the memory of the universe's initial state, less processed and disturbed than the dense regions, offering a cleaner glimpse into the primordial cosmos. And so we are left with a final humbling perspective. Our journey across the cosmos has so often been a quest for light, for stars, for galaxies, for the stuff of existence. We sought to fill in the map, to leave no corner uncharted, but the discovery of the Boötes Void taught us a crucial lesson: the map of nothing is as important as the map of something. It reminds us that our place in the universe is defined not just by our proximity to our Sun or our position within the Milky Way, but by our relationship to this immense overarching structure of filaments and voids. We live on the shores of a great emptiness, a silent neighbour whose existence shapes the evolution and ultimate destiny of our own galactic home. It is a testament to the relentless spirit of human curiosity that we can now gaze into this abyss not with fear, but with purpose. We have transformed the great unknown into our greatest laboratory. The emptiness does not signify an end to discovery. It represents a new beginning, a new environment in which to seek answers to the oldest questions. What is the true nature of the dark universe? What is the final fate of all things? The answers may not be written in the fiery hearts of stars, but whispered in the profound, enduring silence of the cosmic voids. The greatest truths are not always found in the brightest lights. Sometimes they are waiting for us in the dark, in the heart of the magnificent, awe-inspiring, and deeply informative nothingness. The quest to understand the empty zone is the quest to understand everything, and that journey for us has only just begun.